Immunization responds to specific criteria, and some basic principles can be explained to understand how immunization coverage and immunization strategies are set to achieve the maximum objectives. One of the first things that should be kept in mind is that there are two conditions that should be existing at the same time for having a successful transmission of an infectious disease to a host, to the human host. And these two principles, these two requirements are that you need somebody that actually transmits the infection, a source, and therefore there's an exposure to an infection. And at the same time, there should be a host who is susceptible to the infection. In absence of any of these two principles, of these two requirements, infections does not happen. And actually, immunization strategies are set exactly to affect one or both these two conditions. Actually, one of the best ways to explain how immunization strategies can affect the dynamics of infections is explaining and calculating an index, which is R0. R0 actually tells us how the mean number of individuals that can be infected by a single index case in a population where all persons are susceptible. This index is important because actually the ultimate objective of an immunization strategy is decreasing R0 until it becomes less than 1. Because if we achieve this objective, infections cannot be transmitted to more than one person. In the real world, actually, most vaccine-preventable diseases have very high R0 indexes. And what happens is not only that these infections are easily transmitted, but also that age at infection is affected, because the highest is the R0 and the lowest is the mean age at infection before a vaccine is introduced. So having understood which is R0 and having in mind that this index actually explains the dynamics of a population with an infectious disease and possibly a vaccine-preventable disease, let's try to explain the factors that affect R0. There are three components that are very important in producing R0. For example, a constant which is K explains the rate of infective contacts. This depends much on the dynamics of populations, from the pattern of contacts and things like that. Another parameter which in the equation is named beta is about transmission efficiency. And this much depends on the characteristics of the infectious agent and possibly from the host. Third, there's a third parameter, which is D, that explains the duration of infectivity, because the longer the duration of the infectious period and the highest the probability that the infection is transmitted to other hosts, actually. Now, if we think about immunization strategies, we can easily understand that immunization aims at reducing beta, which is transmission efficiency, because it decreases the number of susceptible hosts. But at the same time, we can think that we can affect other parameters of this equation with other strategies. One is isolation and quarantine, that actually decreases and modifies the pattern of contacts among the individuals in a population. And this can be affecting the parameter K. And we can also affect the duration of the infective contact when we have antivirals or antibiotics that can limit and decrease the duration of infectivity and elimination of the pathogen. So immunization is one of the most powerful actions that we can implement for reducing the impact of infectious diseases, but don't forget that we have other means for limiting other parameters that are clearly explained in this equation. Now, R0 is not only explaining the probability and the chance that an infection will be transmitted to other people, but has also some relationship with severity and the balance between the probability of an infection to be transmitted to another individual is not always balanced with the severity of the disease. In this graph, you can see simple representation of different diseases with different R0 values. You should keep in mind that actually, if we have a very severe disease, the chance that and possibly the severe disease will lead to death, the chance and the probability that this disease will be transmitted to other individuals will be low, because simply if the infection is very severe, the disease is very rapidly leading to death, the duration of infectivity is low, and the chance to be of the infection to be transmitted to other individuals will be low as well. At the same time, in case there's a disease in which we have a very long duration of infectivity and a very high value of R0, we will have a very high chance of being transmitted to other individuals. In this graph, for example, you can see that diseases like measles or pertussis have very high R0 values with a severity which is moderate, and I would say high in most of the cases. But diseases like, for example, avian flu have much lower R0 value with a much more severe course of disease. Now, once we understand that one of the main actions that we should try to implement for vaccine strategies is to decrease R0, we should come to the concept of how to increase immunization coverage. We often say that it's very important that immunization coverage is very high. Most of the times the target is 95% of the target population. This is very important, especially when we have to deal with a disease which is transmitted from person to person. And what happens when we increase the immunization coverage is that there's a longer time needed for accumulating susceptibles, and that's why we can wait a longer time between an epidemic starts if we are not able to completely dry the population of susceptible. The other effect when immunization coverage increases is that the mean age of individuals at infection increases. And this is very important because if we start an immunization campaign, for example, and we are not able to reach very high values of immunization coverage, sometimes the effect can be worse than not vaccinating at all. Because if you think about, for example, measles, a modest increase in immunization coverage will not stop the circulation of the disease, but will increase the mean age at infection. And actually, the age at infection is a problem in measles because older individuals experience more severe disease. And the same thing is for varicella and for other examples. So the bottom line here is it's very important that once an immunization strategy is started, it achieves as soon as possible the target coverage, which is most of the times 95% or actually very high in the general population. Well, now, we also are familiar with another concept because vaccines are not 100% effective. We have very high effective vaccines, but efficacy might be 85, 90, 95%. We don't know, and we don't have any vaccine in our hands that is 100% effective. The other point is that we don't have strategies, immunization strategies that can catch 100% of the target populations, for example, 100% of newborns, simply because some of them have contraindications and some of them will miss immunization. So how this problem affects the process of eradication or elimination of the disease is an important concept, because once we start an immunization campaign, even with very high coverage rates, we don't stop the accumulation of susceptible individuals. And they will be accumulated at a much lower rate than when immunization is absent, but actually susceptible will be always there. The process of accumulation of susceptible individuals can be represented graphically by cycles, simply because when an immunization campaign starts, actually it will be able to catch a certain number of individuals in a population, but those not receiving the immunization, or those who will not experience a disease, because actually this is another way to develop a protective status, which is immunized in some way, will be left in the reservoir of susceptible individuals. This will happen in cycles, and actually cycles will be fast if the immunization campaign is absent, will be very low if immunization campaigns will be able to slow down the accumulation of susceptibles. Once the number of susceptibles will be enough to start an outbreak, this will be suddenly coming in, and outbreaks and the development of infection are the other way individuals may develop a protective status opposing to immunization. Obviously, once an outbreak has occurred, most of the people in a certain population will be exposed to infection and will be possibly develop an infection. This will decrease very much the number of susceptible individuals, starting over again a cycle. And obviously, you can think about immunization campaigns as a mean to slow down this cycle, and if you are able to predict the time when this threshold will be reached, the threshold of susceptible individuals, this will be a very important information for adding some immunization actions, which are not traditional campaigns, but can be catch-up strategies or extraordinary campaigns, and so on. In general, the principle is that the threshold for starting an epidemic, given the number of susceptible individuals, is when the number of susceptibles reaches the number of one birth cohort. But there are a number of much more precise mathematical equations that can be used for predicting this threshold. Now, another point which is very important in the transmission and in the dynamics of an infectious disease is the pattern of contacts among individuals. People move, people meet other people, and when you have a disease which is transmitted from one person to another person, the pattern, the number of contacts is extremely important to predict which will be the spread of infection. Thinking of the pattern of contacts, we must think not only about communities where, for example, in schools, we have several individuals in the same environment for a long period of the day, and where the probability of transmitting an infection is high. But actually, think about the easy way when people can move from one country to another country. This also affects the pattern of contacts and is the simple reason why we see outbreaks of infectious diseases that are very rapidly transferred, moved from one continent to another continent. Now, the pattern of contacts is very relevant for immunization strategies because actually we can't always think about isolating a patient, think about Ebola, for example, but the pattern of contacts is important in explaining and in what is herd immunity, because we said that an immunization campaign has the principal objective of immunizing individuals, but at the same time we also want to achieve another objective, which is limiting the circulation of a disease in a certain population. This effect that can be achieved with immunization strategies affects actually the probability that a person will be exposed to an infectious disease. Limiting the circulation of an infectious agent actually gives an advantage to the population targeted for immunization, because the number of persons with infections will be lower, and the circulation of an infectious agent will be decreased, and therefore the probability that actually a person will be exposed to an infection will be lower as well. Actually, the ultimate effect of an immunization strategy is, as we said, decreasing R0 values below 1. Now, thinking of herd immunity, and this is valid for diseases transmitted from person to person only, we can easily represent the dynamic and the transmission of an infection in a graph like the one presented in this slide. This graph presents an example where we are dealing with an infectious disease in a population where all individuals are susceptible and where R0 is 4. This means that one infected individual is able to transmit to 4 additional individuals. This gives you also an idea of the velocity with which an infectious disease may progress. Think about diseases like measles or pertussis, where R0 is nearly 20. This means that actually one individual is able to transmit to other 20 individuals if the population is completely susceptible. In this graph, we are dealing with an infection in which one individual transmits to 4. And in 2 generations, we have scaled up the number of infected individuals very rapidly. Now, what happens if we immunize and we reach in a certain population almost all the individuals? We said in one of the previous part of this lecture that we are never able to reach 100% of persons, and we're never able to have vaccines 100% effective. So we will be left with some individuals that still will be susceptible. But look at the example in this slide. We still have susceptible individuals, but many of them, those actually marked in orange, will be protected simply because they are surrounded by other people that are protected. So they will be not exposed to the infection and even if they're not immunized, they will be protected as well. This effect is herd immunity, and is the added value of extending to very large proportions of our populations the immunization campaign. This is one of the reasons why, even if we have not 100% effective vaccines and we cannot reach 100% of population, we will, however, be able to eradicate and eliminate infectious diseases if we can take advantage of herd immunity. Now, about efficacy, we must also describe a couple of concepts. Before we start an immunization campaign, actually we should have proofs that the tools that we will be used during the campaign will be effective and safe. Every single vaccine is tested in formal randomized controlled trials, and this is done before the vaccines are available in the market and for the use in the community. But remember that after the efficacy has been proved in experimental studies, there are a number of additional studies that are made after the vaccines are implemented in the field. And actually, efficacy can be monitored or tested again and again, even after the experimental studies. And the study designs that can be used for doing that can be observational, most of the times, and this slide actually describes the most popular examples. All these things are needed to confirm that the results of the randomized clinical trials can be applicable to a certain population. And actually, it's very important that these results are confirmed, especially when the local settings may vary compared to the special and protected rules that are followed in clinical trials. Now, when we think about efficacy, we always think about a number which is percent of individuals protected from a disease, which is fine because actually this is exactly what is measured in a randomized clinical trial when we speak about efficacy. And when we think about the percent of individuals protected from a disease compared to unvaccinated individuals. So the concept behind this measure is that we're comparing immunized versus non-immunized individuals, and we're measuring a decrease in incidence of disease. Now, since randomized clinical trials are conducted in ideal conditions, we sometimes need to estimate or to evaluate the effectiveness, what happens in the real world. And that's something that is sometimes obtained with observational studies in post-licensure studies. What happens is that given special results or given some results in randomized clinical trials, we move in the real world and see if actually these results are confirmed. Most of the times, ideal conditions of clinical trials cannot be met in the real world, and effectiveness is generally a little bit lower than efficacy estimated in randomized clinical trials. We can also measure other things, not only the reduction in incidence of the disease, but there are a number of indirect effects of immunizations. These effects may be actually dealing with the reduction in associated disease complications, mortality, even in social measures, we can find out some effects of immunization. One additional thing that can be used for actually measuring the impact of vaccines is the number needed to vaccinate. This is a measure that is not only depending on the efficacy of a vaccine, but it's also depending on the incidence, on the frequency of the disease we want to prevent. So the number needed for preventing one case of meningococcal meningitis, for example, will be much higher than the number of individuals to be vaccinated for preventing one case of influenza, which is much more frequent, simply. Another way to think about the impact and the efficacy of immunizations is immunogenicity. Immunogenicity is not a reduction of incidence, but is a measure about how the individual responds to immunization in terms of antibody titers and levels of antibodies that may protect the individual against the disease. The problem and the important thing to be kept into account is that antibody titers not always predict susceptibility to a disease. We know correlate of protection in most of the vaccine-preventable diseases. We don't know a correlate of protection in others. For example, we are not aware of what threshold is needed of antibodies for protecting an individual against pertussis. So actually, this measure is not very useful when we don't know exactly what a correlation of protection is. Another point is that possibly the higher the concentration of protective antibodies, the longer the protection from a disease. But actually, we still have a number of question marks in the interpretation of immunogenicity results. Another way for representing immunogenicity is how many individuals, when immunized, reach a certain threshold in antibody titers. Actually, this is again useful when we know, for example, which is the threshold, the protective threshold of antibody concentrations. For example, we know it for diphtheria or for tetanus. It's much less useful when we don't know the correlate of protection. Some special way of thinking of protective antibody thresholds, especially for some diseases like Haemophilus influenza invasive diseases, where reaching certain antibody concentrations may predict the susceptibility to the infection. Antibody concentrations and percent of responders have practical use if actually a correlate of protection exists. But one of the things that we actually are trying to extract, to derive from immunogenicity study is which will be the response in time of individuals exposed to immunization. Actually, duration of protection is extremely important to understand how long we should wait before giving a booster dose or if a certain immunization is lifelong, for example. One of the ways to represent, for example, the response that mix together the concept of the percentage of responders and the antibody titers is designing reverse cumulative distribution curves. Actually, it's a very simple distribution in which we put together the antibody concentration and the percent of individuals that reach that antibody concentration. This is useful when you want to test different thresholds for protective antibody concentrations that might predict an effect in the individuals in terms of protection over time. Finally, immunogenicity is possibly one of the most open sciences in vaccinology, simply because we still have a lot of information to to study, and a number of functions depending on specific lymphocyte populations to be cleared, because actually we are fine with antibody concentrations, and traditional immunogenicity studies are mostly based on the function of antibodies. We are much less confident and much less familiar with the measures of efficacy, I would say, or about the role of T and B cells as populations. You know that there are several subpopulations depending on these two lineage, and that they can interact together to produce some effects. For example, we can have no antibody titers detectable in the sera, but actually we can have a prompt challenge when we do a booster dose, for example, in a child or an individual that has been primed with a vaccine. Even in absence of antibodies, we can observe a rapid increase in antibodies once a booster dose is administered. That's actually the effect of memory cells that actually are one of the most interesting things for the future of vaccinology. We're not yet able to measure them with specific standards. A second thing that can be very important in explaining the effect and impact of immunization is the role of innate immunity, which actually also has a major role. So I think that the major advances in immunology will be affecting immunization strategies in a very short time.